All right, so lesson 3 starts on page 12, just so that if you're reviewing, you know where to be. So lesson 3, page 12, we are going to do some simplification, we're going to do some expressions, and we're going to do a lot of crazy algebraic things. So, yay! All right, I know you're groaning, but let's start off simple. Let's start off simple. Simplicity is always good. How would we say this? How would we, if you had to read what I just wrote down, how would you read it?
5 to the first.
Okay, what is its value?
5.
5. Okay, so read this one to me.
5.
5 squared. Or 5 to the second power, either one. Okay, what is its value?
25.
Because?
5 times 5.
Because 5 times 5. Okay, let's do one more. How would we read this one?
5 cubed.
5 cubed, 5 to the third. What's its value?
125.
125. Because?
5 times 5 times 5.
5 times 5 times 5. Awesome, nice job. Okay, so let's start off something easy. Let's see if we can refresh your brain a little bit. What is 7 cubed equal? What does, I should say, 7 cubed equal? You can write it out. You got the information. Remember, it's just 7 times 7 times 7. I'll give you a clue. It starts with a 3 and ends in a 3.
Oh, wait.
No, I didn't. I said it starts with a 3 and ends in a 3. I didn't say the middle number. 343. All right, so now that rule applies even when we're dealing with decimal numbers. So 3/10 to the third power would be what? Oh, we did a third power. Let's change that. Let's do fourth power. 3/10 to the fourth power. What would that equal? Now let's do this one in our head. 3 times 3 is?
9.
9 times 3.
27.
27 times 3. Not 71.
Oh.
If the 1's right, you're 10 off.
27 times 3?
Yeah.
Oh, 81.
81. All right. So we're almost done. How many decimal places are we going to have on this one? Since it's the fourth power.
4.
So 4. So count it out. We have 0.0081. That's our 4 decimal places. All right. Okay. So all I did was I took the 3's, solved it, and then I put my decimal places. You don't have to do it that way. If you feel more comfortable just doing the multiplication and do it all the way down to 4, that's fine too. Either way works. Okay? Not to confuse anybody. All right, let's take a look at a fraction. 1/2 to the 5th power. How do we do that? Because it is this. Well, you know what the numerator is going to be. So we get 1 over 32. Okay, because all we had to do in this case, in this one, since the numerator was 1, all we had to do was multiply the denominator. All right. Now, what about when you are multiplying variables with exponents? It's a little bit different. Okay, so the product rule of exponents, so little terminology here, but I know it shows up on a test, so you got to remember what it is. The product rule of exponents, and you're going to have to get used to this first. When x does not equal 0, get used to that. When x does not equal 0, then x to the m is just a variable, whatever number you can think of, and x to the n, a different variable. When you do that, notice I have x's, right? Those are the same variables, but my exponent variables are different. Okay, so the formula is when I'm multiplying these two variables, since they're the same and have different exponents, all I need to do is add them together. If you recall that from last year. Okay. Oops, I forgot I didn't write it. I did not write that right, even though I said it right. I didn't write it right. All right, m plus n. All right. All right, so that's just the definition. In practice, it looks like this. In practice, it looks like this. Here's x to the 5th times x to the 7th times x squared. What would that equal? X to the 14th. Yep, because all we had to do was add our exponents. And we could do that because our main variable was the same. All right, let's try a different one. How about m to the 3rd times m squared times m to the 4th times n to the 6th power times n to the 7th. So lots of m's, lots of n's. Now you're going to have two answers on this one. I mean, it's one answer, but... Yep. Very good. Very good. All right, so all we have to do now, not bad at all. Let's try a word problem. Okay, because this book is heavy word problem, usually involving the concepts we've just done. Okay, let's take a look at page 14. Okay, so this is already dated because computers advance hugely, and there's actually a law that dictates that, and we'll talk about that not today. But in 2006, so that's a number of years ago already, the fastest computer's performance topped out at about 1 pflops. 1 pflops, don't worry about that. 1 pflops is equal to 10 to the 3rd tflops. Each tflops is equal to 10 to the 12th flops. What was the fastest computer speed in flops? So let's take a look at that. So don't worry about the words. So let's take the information we just said. 1 pflops equals 10 to the 3rd tflops. That's exactly what the problem said, right? 1 tflops, funny term, equals 10 to the 12th flops. Okay? So we want to find the number of flops in 1 pflops. Okay, that's what we need to find. All right? So we have 2 exponents there. What are my 2 exponents? 10 to the 3rd, 10 to the 12th. If I multiply them together, I should be able to find out how many flops that is. So what is 10 to the 3rd times 10 to the 12th equal? 10 to the... Yeah, that's it. That's that simple. Make sense?
Yes.
All we did was we just applied the information. You could do what 10 to the 15th power is if you really want to. There's no need. You would write it 10 to the 15th in normal anyway. All right? This shows an exponential growth, and they've gone much further than that since 2006. All right?